Chapter 4b covers summarising and analysing data. It's from Syllabus Area B, which focuses on data analysis and statistical techniques. Summarising and analysing data is a new section of that area of the syllabus. It's section number 3, and it was added to the syllabus from September 2019. Let's have a look at each of the detailed learning outcomes from this new part of the syllabus. Okay, firstly we need to be able to calculate a few things. So we need to be able to calculate something called the mean, call that number 1. We also need to be able to calculate the mode. And then thirdly, we need to be able to calculate the median. And we need to be able to do that for both grouped and ungrouped data. So as we work our way through the chapter, we'll make sure that we understand the terminology and that we're also able to perform the calculations. We then need to be able to move on and do some other calculations. So we need to be able to calculate measures of dispersion, which again we'll explain as we start to work through the syllabus. And it specifically mentions that we need to be able to calculate something called the variance, secondly the standard deviation, and thirdly the coefficient of variation. And again we need to be able to do that for both grouped and ungrouped data. The third learning outcome again focuses on calculation. We need to be able to calculate something called expected values that will be used for decision making, and we'll cover decision making in more detail later on in the course. We then need to be able to explain, so note that the verb has changed here, so moving away from calculation now onto explanation, and we need to be able to explain the properties of normal distribution. We then see another verb focusing on interpretation, so we need to be able to interpret a normal distribution graph and the normal distribution tables. Finally, if we think about this part of the syllabus in relation to the exam, as we mentioned, it forms part of the data analysis and statistical techniques section of the syllabus, so Syllabus Area B. It is important that we can follow through the calculations and meet each of the learning outcomes, as these could be tested in section A of the examination. So we'll see this area of the syllabus tested through objective testing questions. Okay, let's start to work through each of the learning outcomes individually. We can see that the summary diagram covers each of the key learning outcomes. So there are some calculations that we need to be comfortable with. We need to be able to calculate the mean, the median, and the mode. We also said that we needed to be able to do some calculations in relation to dispersed data. So we need to be able to calculate the variance, the standard deviation, and the coefficient of variation. The third learning outcome in relation to calculations covered expected values. And then we needed to be able to explain and interpret normal distribution graphs and tables. Let's work through each in turn. So the syllabus learning outcomes refer to being able to do the calculations in relation to both grouped and ungrouped data. So we'll start by defining each of them. Group data, as it states here, is where the frequency is shown in terms of a range, and it's often known as continuous data. And this is where we take the information that has been collected and recorded and we organise it into groups, so possibly bands or classes from the raw data. And we'll see that in the example that we're going to consider in a second. Ungrouped data, on the other hand, is raw data that has been collected but not sorted into any group or class. Now normally, if there is a large set of data, it's often more convenient to group it into frequencies. And what we mean by that is grouping it together into either bands or classes. And as I said, we're going to see that below in the example that we're going to use throughout the chapter. Syllabus Learning Outcome 1 talked about being able to do some calculations in relation to averages. So we noted that we needed to be able to calculate the mean, the median and the mode. So it's important that we know the definition of each and that we can also do the calculations. We're going to use an example to work through each of those calculations, and the example that we're using is in relation to annual mileage travelled. So here we have the small town of Brumbrum in the West Midlands, and we had a survey of 1,600 out of 100,000 car owners to find out about the annual mileage travel. We have the results categorised below. So this is a good example of grouped data. And the reason that we know that it is grouped data is because it is grouped into bands here. So we have certain bands based on mileage. So we can see that we have the first band is less than 2,000 miles. Our second band is then between 2,000 and 4,000 miles. And we can see that those bands carry on to the last one, which is greater than 16,000 miles. Now, what happens when we group data is we lose the individual data. So we can see here that we had 10 cars in total who travelled less than 2,000 miles. And we talk about the midpoint being 1,000, so that's the midpoint between 0 and 2,000. So we know that 10 cars did travel less than 2,000 miles, but we've lost the individual detail of those 10 cars. We don't know exactly how much mileage they travelled, but as we said, it is useful to be able to group this data when there's a large amount of information. So if we had this list detailing all 1,600 drivers separately, then obviously that list would be very long. There would be a huge amount of information for us to work through. But by grouping the data into bands, we can see that we can analyse the data much more easily. Okay, so what we've got here is the midpoint mileage for each of the bands. So as we said, the first one is 1,000, the second is 3,000, so that is our midpoint between 2 and 4, and it carries on as such. We then have the number of cars that recorded that band of mileage. And then in the end column, we've taken the frequency, so the number of cars, times the midpoint to give us our total here. So for example, we've taken the midpoint mileage of 1,000. We had 10 cars that recorded that, so that gives us 10,000. We've taken the midpoint mileage of 3. We had 14 cars that recorded that, which gave us 42,000. Okay, we're going to work with this information as we go through the calculations, and we're going to explain and calculate the mean, the median and the mode to make sure that you can meet the first learning outcome. The first calculation that we look at is the mean. And the mean is the average value. It's widely understood. So it's the average that we get by calculating or adding together all of the observations and dividing it by the number of observations. So you're probably comfortable with that. You've probably done average calculations quite a lot through your studies, where we're just going to take the total on the top, the total sum on the top, and then divide it by the number on the bottom. You do get the formula in the exam, so you get it for both ungrouped and grouped data. So just make sure that you're comfortable using the formula sheet and be happy that it is there with you in the exam. And as you can see, we have for ungrouped data, we simply have the sum on the top. So this sign here denotes the sum. So we have the sum of the observations, which is x, and then n stands for the number of observations. We can see with group data it is slightly different. So instead of just being EX on the top, we have EFX. So that is the sum of the frequency multiplied by the value. And when the frequency is a group distribution, like what we've seen for the mileage, we use the midpoint for X to calculate the mean. So in other words, if we go back up to the table here, we're going to take fx as being the midpoint, which is x, multiplied by the frequency, which is the number of cars that drove that midpoint, and then we will multiply the two together. So when we calculate the mean, we take the sum of fx, which is going to be our total mileage when we add them all together, and we're going to divide it by the number of observations. And the number of observations, again, is based on the sum of the frequency here. Okay, let's do it together. If we flip over the page, we'll see that we have our first lecture example, and it's asking us to use the information in 2.1 to calculate the mean annual mileage for these 1,600 cars. Now, you don't really need to use the formula if you're comfortable with the understanding of the mean, so you know that it is an average calculation. But just for completeness here, let's note down the formula. And again, remember that we get it in the exam. So the mean is equal to the sum of the frequency multiplied by the value divided by the sum of the frequency. As we said, by looking at the information in relation to the data at 2.1, the total mileage is 14,956. So that's the total amount divided by all cars, or all observations if you like. So we're going to divide it by the 1,600 number of drivers that we had gathered the data for. That would give us the mean annual mileage for all car owners, which would be 9,347.5. So 9,347.5 is the average number of miles driven by or travelled by all car owners over the year. What we're not saying here is we're not saying that each individual driver covered 9,347.5 miles. That's not what the mean is saying. It's just saying that it is an average by taking all of the observations that we've recorded. So by looking at all 1,600 drivers, we're saying that the average mileage covered is 9,347.5. Okay, bear in mind what we said. This will appear in section A of the paper if it comes up, so it will be an OT question. So it's likely to be a relatively straightforward calculation where you will be asked to calculate the mean, you'll be given the data and the observations, and you just need to know that it's the sum of the total on the top divided by the number of observations on the bottom. The second calculation that we need to be comfortable with is being able to calculate the mode. And the mode is the most frequently occurring item. So in other words, if we think about the mileage, it is the mileage that is driven by the greatest number of drivers. Yep, so it's the most frequently occurring item. If we did have ungrouped data, we just simply pick the most frequently occurring item, and we'll see that in the OT style lecture example that we're going to look at in a second. However, with group data, like what we have in relation to the mileage for the drivers, we can't actually say what the most frequently occurring item is. Because remember we said when we group data, we do lose some of its detail. So because we've grouped it into bands, for example, we have the first bandage of mileage was less than 2,000, and we had 10 drivers who covered less than 2,000 miles. But we don't know within there what actual mileage those 10 drivers covered. Some of them could have covered, say, 200, somebody could have covered 1,900. We don't know because the detailed information is now lost within that band. It is a band of less than 2,000 miles. So therefore we are unable to say what the most frequently occurring item is from group data. However, we can overcome that issue by estimating the mode using something called a histogram. And a histogram is a graphical representation of the frequency of the data that we're given. So here it gives us a three-step process to find the mode using a histogram. So we firstly have to draw the frequency histogram to identify the highest frequency class. So in other words, within those bands. We then draw a diagonal line from the top of that block either side of the highest class. We then need to intercept the estimated modal value and we read it from the x-axis. Now, because your exam is OT style, you're not going to be asked to draw a histogram, so therefore it could be more likely that you see an OT question focusing on ungrouped data, so that you don't have to use the histogram, and we'll see that in a lecture example in a wee second. But what they could ask you to do is maybe to interpret a histogram if they have given you the information in relation to group data. So let's just make sure that we can do that. We won't obviously be asked to draw it, but let's just make sure that we can interpret a histogram. Okay, so here we have an example of finding the mode using a histogram, and again this is using the information that we collated at section 2.1 in relation to the mileage. If we just understand what the graph is showing here, so we can see at the bottom we have our midpoint mileage which has been recorded, and then we can see that we have on the y-axis the number of cars. We can see that then the information has been plotted onto the histogram in relation to the different bands. So with a midpoint of 1,000, remember there was 10 drivers. With a midpoint of 3,000 there was 14. With a midpoint of 5,000 there was 154 drivers. With a midpoint of 7,000 there was 292. We can see that the most frequent midpoint was at 9,000 and there was 493 drivers within that band, 404 in the next band, and then 164, 48 and 21 finally recorded at the last band. Okay, and we can see that this information has already been plotted onto the graph or the histogram for us. And then to find the mode, so the most frequently occurring mileage, we can see that that information can be picked up from the x-axis. The x-axis is here, and obviously the vertical is the y-axis and the horizontal is the x-axis, and we can see that the mode can be estimated at approximately 9,250 miles. Now, as I said, I think it's probably quite unlikely that you will see the mode in relation to group data. It's probably more likely that you'll see it in relation to ungrouped data because it's obviously much easier to calculate here. So lecture example 2 is indicative of an OT style question. So yes, be able to interpret a histogram, but you won't have to draw one. But let's see how we could see this examined via a numerical OT style question. Okay, so again, reading the requirement first here, which is always important in the exam, so identifying what we're being asked to do. It says, what is the number of loaves needed per shopper in the 1 week period? And bearing in mind that the mode is the most frequently occurring item. If we read through the information, we're told that a group of shoppers were interviewed and asked how many loaves of bread they would need to buy from the bakers over a 1 week period. The results are as follows, and we'll see that we have each of the individual responses recorded here, so the information has not been grouped. This is ungrouped data. So we have the information for 0, 1, 2, 3, 4, 5 and 6 loaves separately. We're then given the number of shoppers who bought each amount of loaves, and the mode is the most frequently occurring item, and therefore we can see that the most frequently occurring item is 4, because that's the greatest number of shoppers that acquired those number of loaves. So therefore the mode, the answer we would provide here, would be 4. The most frequently occurring item is 4. 4 is the most frequent number of loaves that are bought in a 1 week period. The third and final calculation to meet the first learning outcome is to be able to calculate the median. If we firstly look at the definition, and then we'll work through the calculation using an example, the median is the value of the middle item. So what we mean by that is it's the middle item of a set of data, and it would be shown as the midpoint when that set of numbers is written out in order. So in other words, when we write the numbers out in order from, say, the lowest to the highest number, the median will be the middle item of that set of data. If we're looking at ungrouped data, we need to think about whether we are considering an odd number or an even number, because the way we do the calculation will be slightly different depending on whether it's an odd number or an even number. And what we mean by that is the number of items in the set. So for example, if we have a data set that has 7 items, that would obviously be an odd number. And if we have a data set that has 8 items, that would be an even number. So the first thing that we want to do is we want to arrange the data in order. So as we said, from the lowest to the highest point. And then we want to calculate the median or the middle item by using one of 2 methods, depending on whether it is an odd or an even number. When we talk about n is the number of items in the data set. So that would be either the odd or the even number. So here we would take 7, for example, plus 1, which would give us 8, divided by 2, which would give us 4. So the 4th item in the list would be the median or the middle item. If we have grouped data, that data will normally already be in order, but it will be in order in relation to ranges. So again, remember, we lose some of the individual detail when we group the data, but it will be grouped in order of ranges, and then again we note the middle item. Much easier to explain with an example. So let's look at lecture example 3, which is indicative of an OT style question, and here we're asked to calculate the median value, or it states what is the median value of earnings. Okay, so here we have a supermarket, we have the number of employees and the annual earnings per employee, and we are given that information. We're given the earnings separately. So this is an example of ungrouped data. Yeah, so it's not grouped into ranges. We're not told less than 5,000 and between 5 and 10,000. We're given the individual items. So we're told that 3 employees earn 6,000, 5 employees earn 7,000, etc., etc. We need to look at the number of items in the data set. So if we add them up, if we take 3 plus 5 plus 3 plus 1 plus 2 plus 1, we have a total of 15 numbers in the data set. And 15 is obviously an odd number. And as we said, we need to organise the data, so we need to look at it from the lowest to the highest, and we can see that that's actually already been done for us. So it has been ranked from the lowest to the highest. But what we need to do is we need to look and see, well, what is the cumulative number, so that we can start to see what the middle item is. So what I mean by that is we had 3 employees earning 6,000, and then we had another 5, so we have a cumulative of 8 employees, and then we have another 3, so we have a cumulative of 11 and 12 and 14 and 15. So we have 15 items in total. To calculate the median, we said we wanted to take the number of items in the data set. We wanted to add on 1 and divide it by 2. So the number of items in the data set is 15. We add on 1, which gives us 16, and we divide it by 2, which would give us 8. So that therefore means that the 8th item is the middle item. So if we go back up to the information, we want to look and see what is the 8th item recorded. Yeah, so the middle item, if you think about recording all 15 separately from the lowest, which is 6,000, up to 15,000, which is the highest, and if we plotted them all out separately, when we get to the 8th item, that is the middle item of the data set, starting with the lowest of 6 and going up to 15,000, we have 15 items in total, and therefore the median value of earnings, the middle value of earnings that falls at the 8th item, is 7,000. So to answer the question, we would type 7,000 into the answer box. It's also useful to know the advantages and disadvantages of the mean, the mode and the median. However, do bear in mind that the syllabus learning outcome asks you to calculate each of them. But as I said, it's useful to know the advantages and disadvantages also. If we look at the mean, firstly, we can see that the advantage of the mean is that it's used most frequently, so it's something that is understood by most people. It is the average, and it is the average that brings in all items of the data. So we're all used to calculating an average. If you said the average or calculate the average to someone, they would understand what you mean. The downsides of it is it may not be a value in the distribution. So what we mean by that is that average item may not be an actual item. So for example, when we calculated the average mileage from all of the drivers, it dropped out at 9,347.5. We said that was the average of the 1,600 cars that we had recorded the data for. But that 9,347.5 might not be the actual mileage driven by any of those drivers. It's just an averaging calculation. It can also be distorted by extremely high or low values. So again, if we use the example of mileage, one recording of a very, very high mileage will push that average up significantly. And finally, it ignores dispersion, and dispersion is a key term that we're going to start to consider. And we can see that the fact that it ignores dispersion is a disadvantage of the mean, the mode, again it says it ignores dispersion, and the median as well, it ignores dispersion. So it's actually quite useful to define dispersion firstly here. So we'll see that we have a definition of dispersion in your notes, and it's a limitation, as we said, or a disadvantage of the mean, the mode and the median. And the averages that we've calculated here don't explain very much about the distribution itself. So what we mean by that is we can't determine whether that item or that data lies close to the average. So is it close to the central point or the mean, or is it scattered around the entire range of possible values? And that's what we mean by dispersion. Quite often it's known as the variability or the spread. And measures of dispersion give us some idea of the spread of a variable about its average or mean. We're going to look at calculations that involve dispersion in more detail, but let's just finish off by considering the advantages and disadvantages of each of the mean, the mode and the median. So we've covered the mean. Let's look at the mode. The advantage of the mode is it's the most popular item, so we can see very clearly what the most popular item is from the data set, and that won't be distorted by high or low values. So it's not a spread, it's not an average, it's just that individual most popular item, and it does correspond to an actual value in the distribution. So when we looked at calculating the mode for the loaves of breads, we've seen that 4 was the most popular number of loaves of bread to be bought within 1 week, and that was an actual value. Again, it ignores dispersion, as we've just mentioned, and it may not take account of all of the data. So again, we're not looking at an average of everything, we're just focusing on that one individual item. Finally, if we look at the median again is not distorted by high or low values because it's not taking an average of all of the data set, and again it corresponds to an actual value. It's the actual middle item from the data set. But again, because it ignores dispersion, which we said is the variability of the spread, then again it has a limited use. Okay, so let's consider dispersion in more detail. And as we said, measures of dispersion give some indication of the spread of the data around a central point. That central point we now know is called the mean or the average. Okay, let's look at dispersion now. So we're now moving on to the second learning outcome from the chapter, where we need to be able to calculate measures of dispersion, including the variance, the standard deviation, and the coefficient of variation. As we said, dispersion measures the spread of data around the mean, and the most important measure of dispersion is the standard deviation. You get the formula in the exam, so we are given 2 formula in the exam for individual data items and for a frequency distribution, like the information that we were given in the mileage table in lecture example 1. Okay, so we're going to look at calculating the standard deviation together, and as we said, it measures the spread of data around the mean. So what we mean by that is how close is all the data to the average. If we have a low standard deviation, it means that the data points are close to the average, and if we have a high standard deviation, the data is not close to the average. Using standard deviation, we have a standard way of knowing what is normal and what is perhaps extra high mileage, for example, or extra low mileage. We'll then move on to calculate the coefficient of variation, which is actually a more meaningful number and will let us understand the standard deviation in a bit more detail. But let's start by calculating the standard deviation, and we're going to do that by using the information that we gathered in lecture example 1. So we're going to complete the following table here and calculate the standard deviation. Now the standard deviation is denoted by the Greek letter sigma. So we're going to complete the table that we had started to pull together in lecture example 1. You can see that we have the same information here. We're now just given the information in thousands. So our midpoint was 1,000, there was 10 cars. You can flip back to lecture example 1 and you'll see this is the same information. The midpoint of 3,000 had 14 cars. What I'd like you to do is to complete the following table. So you might want to pause the recording in a wee second to enable you to do that. So we want to take f times x. So let me do the first couple of lines with you just to get you going. So f times x would be 10. So that was our 10,000. Yep, so 1 times 10. 1,000 times 10 would give us our 10,000. X squared, so remember x here is our midpoint, so if we take 1 and square it, so remember squaring a number is multiplying it by itself, so 1 times 1 would give us 1, and then if we take f times x squared, that would be 10 times 1, which would give us 10. Let's do it for the second line just so that we fully understand what we're doing. Okay, so fx is f times x, so that would be our 3 times our 14, which would give us 42. X squared would be our 3 squared, so 3 times 3 would give us 9. And then our fx squared would be our f times our x squared, so our f here is 14 times our x squared, which is 9. So again, if I just note it in a bracket here so that you can follow through, we do 14 times 9, which would give us 126. Okay, you might want to pause the recording now and complete the table, and then we'll calculate the standard deviation together. Okay, if you want to check your workings with the completed table, and there's a few numbers from this table that we will need to take forward into our standard deviation calculation. So remember, the formula you do get in the exam, it is on the formula sheet. We're reminded of it here. So there's a couple of numbers from the table that we need to take forward. So we need the sum of fx squared, which is our 151,696. So let's just denote that next to it, the sum of fx squared. We also need the sum of f, which is our 1600, our total number of items that we have in the data set. And we also need the mean. So remember, the x with the wee line above it is the mean, so we need the mean squared. And remember, we calculated the mean in lecture example 1, and the mean number of miles was 9,347.5. But remember now, to keep everything nice and neat, we've transferred all of our data into thousands. So we need to make sure that we are consistent. And when we plug the mean into the calculation, it will now become 9.3475, so that we're working in thousands. Okay, if we see through the calculation then, so we can see that the workings are given for us here. We're picking up these 3 numbers that we've just pulled out. Let's take it forward into the formula, and again, if you want to grab your calculator, you can do this calculation with us. So we can see that we take the 151,696 on the top, we divide it by the 1600 on the bottom. We then deduct the mean squared, so we need to work out 9.3475 squared, and again just reminding you that all of our calculations are in thousands, and that would give us a standard deviation. So again, you might want to pause the recording here and just make sure that you can work through the calculations. Don't forget to hit your square root button, quite often students do that. So making sure that you hit your square root button at the end, and that would give us a standard deviation of 2.72658. And if we transferred that back into thousands, our standard deviation in miles to the nearest mile would be 2,727. Okay, to interpret that information, to make it a bit more meaningful to us, we're going to go on and calculate the coefficient of variation next. Okay, so we also need to be able to calculate the coefficient of variation, and I also think that the coefficient of variation helps us to understand the standard deviation a wee bit better, because it measures the standard deviation as a percentage, and it measures it as a percentage of the mean. A key learning point here is that the higher the percentage, the higher the dispersion, or the higher the spread, and therefore the lower the percentage, the lower the spread. So in other words, if we have a low coefficient of variation, it means that the majority of data is close to the mean. So let's do the calculation using, again, the information on the mileage that we've been carrying forward from lecture example 1. Now this time you don't get the formula in the exam, so this is one that you do have to learn. And the coefficient of variation, you can either learn it as a formula or understand what it means. To understand what it means, we said it's the standard deviation as a percentage of the mean. So therefore, as the formula, we take the standard deviation on the top, our sigma, and then we put the mean on the bottom. Okay, let's carry on with the information from lecture example 4, which was bringing forward all the information on mileage. So we worked out that the standard deviation was 2,727, if we say it just rounded, and the mean was 9,347.5. If we take one over the other, so the standard deviation divided by the mean, we get 0.29, which is 29%. And remember, we said a low percentage means a low dispersion. So that actually means that the majority of data is close to the mean. So we do have a low percentage here. We have 29%, so it's less than our sort of 50% halfway mark, if you like. So a lower percentage of 29% means that most drivers cover a mileage close to the mean. So in other words, most drivers cover a mileage close to 9,347.5. And that should make sense to us, because if we go back to the information, that original table that we were given in section point 2 of your notes, we'll see that the majority of drivers did cover a mileage close to 9,000. So we can see that 292 cars covered 7,000, 493 cars covered 9,000, 404 cars covered 11,000. So the majority of drivers, or the majority of data, is close to the mean. And that's the useful understanding behind the coefficient of variation. Okay, the last thing that you could be asked to calculate is the variance. So again, this is something that you will need to know as opposed to being given in the formula sheet. And the variance is the standard deviation squared. Yep, so in other words, you multiply the standard deviation by itself. So the variance is equal to the standard deviation squared, and therefore the inverse of that, the standard deviation, is equal to the square root of the variance. Just watch out for that in questions. So a wee reminder here, watch out in questions whether they give you the variance or the standard deviation. So if they give you the variance but you need the standard deviation, then you take the square root of the variance to get the standard deviation, and vice versa. If they give you the standard deviation and you need the variance, then you take the standard deviation and you square it to calculate the variance. Learning outcome number 3 is to be able to use expected values for decision making. So you need to be able to calculate an expected value. An expected value is a weighted average. So we've already seen the average, we've seen the mean, but the expected value is a weighted average, and that weighted average is based on probabilities. Using expected values is useful when there's a number of possible outcomes from a single event, but it's not known with certainty what will actually happen. So what we often do in relation to decision making is we assign a probability to each of the possible outcomes. So let's say, for example, we were looking at opening, I don't know, a new theme park, and we were a bit unsure about demand. So we weren't sure whether demand would be, let's say, low, medium or high. We could assign probabilities to each of those possible outcomes. So we could assign a probability to say, let's say there's a 30% chance that demand would be low. There may be a 50% chance that demand is medium, and there's a 20% chance that demand is high. And we could use those probabilities and assign them to the different revenue outcomes that could arise under each of the demand situations. And that would enable us to calculate an expected value revenue. And basically what that expected value does is it takes into account all of the different possibilities, all of the different possible outcomes that could arise from opening the theme park. And it's useful to calculate an expected value for decision making. As we said, syllabus learning outcome 3, you need to be able to calculate an expected value. Now there's a formula that you get in the exam, it's with you on exam day, so again just being comfortable with pulling that formula from your formula sheet, and it's where you take the sum of the probability of the outcome occurring and you multiply it by that outcome. Let's look at lecture example 6 and we'll see if we can calculate an expected value together. So lecture example 6 is indicative of what we could see as an OT question in section A of the exam. If we read the requirement first, it asks us what is the expected value of the gambler's winnings. Now we do get a formula in the exam which you can use, and that formula might help you until you get used to doing an expected value calculation, but it is relatively straightforward. So as we said, we're going to take the sum of the probability of the outcome multiplied by the outcome or the result. So let's look at the data that we've gathered here. A gambler has placed a bet on a horse. From past information, the probability distribution relating to its chances in the race are as follows. So the fact that the horse will come first and there will be winnings of 100, there is a probability of 5%. Second, we will win 50 and a probability of 15% of that happening. Third, 25 and a 10% probability, and no place at all, there would be no winnings, and there's a 70% probability of that happening. So to get the expected value, we need to multiply the result by the probability and then add them all up to get the sum of the outcome. Okay, so we can use the formula if you wish, or once you get used to it, it's a relatively straightforward calculation. So if we do 100 times 5%, so again remember that 5% would be put through your calculator as 0.05. Yep, so if we go 100 times 0.05, we get 5 in total. If we do 50 times 15%, we get 7.5. And if we do 25 times 10%, we get 2.5. And finally, 0 times 70% would give us 0. If we add them all up, we get an expected value of 15. So the expected value of the gambler's winnings is £15. The learning outcome just asks us to calculate an expected value, but again it is useful to know some of the limitations. That expected value is a long run average result, so it's not the actual outcome, but it's based on the long run average, and therefore it could be inappropriate for a one-off decision. So as we've seen with the gambler and the outcome of the horse coming as the different places, it was based on past information. It's heavily dependent on the probability distribution, so we can see that our expected value was very low at 15. So if it did come first place, we would win 100, but our expected value came out very low at 15, and that was because the probability distribution, there was a 70% chance of us winning nothing, and therefore that pulls down the expected value significantly. The final limitation is that expected value ignores risk, and the risk is the spread or the variability of the outcomes. The final two learning outcomes expect you to be able to explain and interpret the properties of normal distribution, and that's what we're going to look at now in our final section, section 5. The normal distribution, sometimes known as the probability distribution, is a frequency distribution, and it's important because it arises in lots of real life situations. So here we're going to look at an example where we're going to consider the height of people in the UK. So if we took the population of the UK and looked at a distribution of the height of all adults in the UK, it would almost certainly follow a normal distribution. In fact, most data distributions follow a normal distribution, and what we actually mean by that is that the majority of items will lie near to the average, which we now know is also called the mean. So when we look at a data distribution, if the majority of items lie near to the average, we say that that data follows a normal distribution. If we apply that to the height of adults in the UK, if we recorded the height of all adults in the UK and we also recorded the average height of an adult in the UK, we would see that the majority of adults will be near to that average height or mean, and therefore show that it follows a normal distribution. A normal distribution is often described as a bell-shaped curve, and that's what we're going to look at next. So again, if we consider the situation of adults in the UK, we can record the average height. So the average height we're going to denote using the symbol U, and the average height of all adults in the UK is 1.7 metres. We can also record the standard deviation using sigma, and the standard deviation is 10 centimetres. And what we can see in this bell-shaped curve is that a normal distribution is always symmetrical around the mean. And what we mean by that is 50% of the data will sit above the mean and 50% of the data will sit below the mean. So in other words, 50% of adults in the UK will be taller than 1.7 metres and 50% of adults in the UK will be smaller than 1.7 metres. What we can also interpret from this bell-shaped curve is that the majority of data items will lie closer to the mean. So when we record the height of all adults, we will see that the majority of that data will sit very close to the mean, and we can see that the occurrences will fall as we move away from the mean. So yes, there will be adults in the UK who are maybe greater than 2 metres, but the occurrences of those adults will be much lower than those who are close to 1.7 metres. We can also see that when we look at the other side of the curve. So again, the occurrences of adults that are shorter than 1.7 metres starts to fall as we move away from the mean. On this next page, we're just going to remind you of some of the key things that we've discussed so far in relation to interpreting the normal distribution, because remember, that's one of your key learning outcomes, that you need to be able to interpret the properties of normal distribution. So remember, we are using the U to define the mean. We're using sigma to define the standard deviation, and putting that information into the data that we've used so far. The average height of an adult in the UK is 1.7 metres and the standard deviation is 10 centimetres. And we're going to go on and explain what that standard deviation means in a bit more detail in a second. The reason that the shape of the curve is bell-shaped, again, we've covered this already, but just to remind you that the majority of people's heights in the UK will lie very close to the average height or the mean. So in other words, we say the majority of the UK population will be close to 1.7 metres. And we've seen that in the graph, that there is a higher concentration of occurrences as we get closer to the mean. As we get further away from the mean, the number of people with heights gets much lower, and therefore the curve starts to balance off. When you're attempting questions in the exam, it's important that you understand this. So it's important to note that the normal distribution is always symmetrical around the mean. So what we mean by that is 50% of adults in the UK will be taller than 1.7 metres and 50% of adults in the UK will be smaller than 1.7 metres. Okay, let's start to understand the properties of normal distribution in a little bit more detail. So again, just reiterating what we've already said, but this is important. The curve is symmetrical and it's centred around the mean or the average. As we've just explained, what does that mean? Well, it means that 50% of the UK population are taller than 1.7 metres and 50% are shorter than 1.7 metres. The total area under the curve will represent 100% of the population. So what we mean by that is that everything underneath the bell-shaped curve will represent all data items. So in other words, 100% of the population will fall under the curve. The width of the curve is measured in terms of standard deviation. And we said that one standard deviation was 10 centimetres, but if the width of the curve is measured by standard deviation, what is really helpful for us from a practical point of view is to know that under the normal distribution curve, there is a range of 6 standard deviations. And that can be really helpful for practical purposes because that can help us to interpret the data in more detail. So let's put it into practice with our example here. So we're saying the range under the curve is 6 standard deviations. So that basically means that 3 standard deviations will sit below the mean and 3 standard deviations will sit above the mean. So let's use that to interpret the information. So it can now tell us the range of adults' heights in the UK because we know that one standard deviation is 10 centimetres. So if 3 standard deviations sit below the mean, we can then work out that the range of adults, our smallest data item, or our lowest value, if you like, will be 1.4 metres. So we'll take the average or the mean of 1.7 and we will deduct 3 standard deviations. So 3 times 10 centimetres to get us down to 1.4 metres. So at one end of the curve, we can say that our lowest height is 1.4 metres. At the other end of the curve, we will add on 3 standard deviations and therefore our highest height is 2 metres. And there will obviously be occasional exceptions, so there will be some very, very tall people who are taller than 2 metres, but as a whole, what this normal distribution represents is that the majority of people will sit within the bell-shaped curve. So in other words, the majority of adults in the UK will sit within the range of 1.4 metres and 2 metres. This can be really useful information because it will allow us to use normal distribution tables to work out the percentage of the population that are exactly a particular height. So for example, if we wanted to work out what percentage of the UK population were 1.6 metres, we can use the properties of the normal distribution curve along with normal distribution tables to enable us to identify that percentage. And that can be a really useful feature that we can apply to many situations. Let's look at some examples then. Okay, let's start to see how we can interpret normal distribution graphs and tables, because that's one of the key syllabus learning outcomes that you need to be comfortable with. So we'll continue with our example where we're using a standard deviation of 10 centimetres, and remember we had an average or a mean height of adults in the UK of 1.7 metres. And let's say we wanted to establish the percentage of the population that were taller than a particular height. So just to remind you of some of the properties of a normal distribution curve. So remember we said that the curve would always be symmetrical and 50% of the data items would sit above the mean, 50% of the data items would sit below the mean, and also that there would be 6 standard deviations underneath the curve, and therefore 3 standard deviations above the mean and 3 standard deviations below the mean. In this example, we are going to use a standard deviation of 1.96. So we want to try and work out what is the percentage of the population who are 1.96 standard deviations greater than the mean. Let's put that into context here then. So we said that the mean was 1.7 meters. The standard deviation is 10 centimeters. So we are basically wanting to establish the percentage of the population that are 1.96 standard deviations above the mean, or in other words, the percentage of the population that are taller than 1.896 meters. And we can use our normal distribution tables to tell us the answer to that question. So what would be the percentage of the population that are taller than 1.896 meters or 1.96 standard deviations from the mean? Okay, let's go to our normal distribution tables and start to see how we can interpret this information. So you get your standard normal distribution tables in the exam, and remember we wanted to assess 1.96 standard deviations from the mean. So if we go down the first column of the table, and here we can see 1.9, but we don't want just 1.9, we want 1.96. So now we're going to read across the top row until we get to 0.06. So that would give us 1.96. Yeah, and if we pick up the number from our normal distribution tables, we can see a number of 0.4750. Now what that 0.4750 represents is a percentage. So if we go back and look at our graph here, we can see that the area under the curve that represents 1.96 standard deviations also represents 47.5% of the population, because that's what the number 0.475 from our table represents. We reminded you earlier that the area under the curve adds up to 100% and 50% sits above the mean. So if 47.5% of the population sit within 1.96 standard deviations of the mean, that then says to me that 2.5% of the population sit above this height. So that can be really useful to be able to analyse data sets, because now we can say that in this example, this actually means that 2.5% of the population are taller than 1.896 meters, or 2.5% of the population sit outside, if you like, 1.96 standard deviations of the mean. And that's what we need to be able to do in the exam. We need to be able to interpret this type of information. So it might be worth pausing the recording and going back through this again, just to make sure that you can use the standard normal distribution tables and that you can start to interpret the information that comes from that. Okay, let's look at a second example then, just to confirm our understanding. And this time we're going to measure a range of 1 standard deviation from the mean. So again, if we just remind ourselves of the information on the graph, we know that the average height of an adult in the UK is 1.7 metres. We know that a standard deviation is equal to 10 centimetres, and now we want to measure the range of 1 standard deviation from the mean. So in other words, we want to look at a height of 1.8 metres. And we want to be able to interpret the percentage of the UK population who are taller than 1.8 metres, and the percentage of the UK population who are smaller than 1.8 metres. And we can do that using our normal distribution tables. So remember, from our normal distribution tables, we can get a measure of the standard deviation. And that standard deviation that we want to assess here is 1 standard deviation. So let's go on to our normal distribution tables together. Remember, you get these in the exam. And if we look at 1 standard deviation, we can see a figure here of 0.3413. And remember, that figure we take forward into our analysis as a percentage. So in other words, 1 standard deviation represents 34.13%. So if we go back onto our graph here, we can see that the area that represents 1 standard deviation is 34.13%. If we want to interpret the amount of people in the UK who are shorter than 1.8 metres, so remember, 1.8 metres is 1 standard deviation away from the mean. The whole area under the curve represents 100%. So if we want to look at everybody who is below 1.8 metres, that will show everything under the area of the curve that we are now shading here. So therefore, we can take our 50% that sit below the mean plus the 34.13% that sit within 1 standard deviation from the mean, and we can interpret that 84.13% of the population are shorter than 1.8 metres. Therefore, we can also say, because we know that the area under the curve represents 100%, we can also say that 15.87% of the population are taller than 1.8 metres. Okay, and then we have one final example. Again, just confirming your understanding. So you might want to pause the recording here and see if you can use the normal distribution tables yourself this time to interpret the information. And this time we're measuring 2 standard deviations from the mean. Yep, so it's helpful to start by just plotting your information on. So the mean is 1.7 metres. A standard deviation is 10 centimetres. So now we're looking at a height of 1.9 metres, and we want to be able to interpret the percentage of the UK population who are shorter than 1.9 metres and the percentage that are taller than 1.9 metres. Okay, pause the recording and see if you can interpret the data from the tables. Okay, so let's look now at the tables together. So again, we want to pick up 2 standard deviations. So from the tables, the number from 2 standard deviations is 0.4772. Again, we take that forward into our information. The 0.4772 translates into a percentage. We have 50% below the mean, plus the 47.72% that sit within 2 standard deviations from the mean. So again, we can interpret that 97.72% of the population are shorter than 1.9 metres and 2.28% are taller. Okay, and we can use this information basically to interpret any data sets. So here obviously we're just looking at the height of the UK population, but it can be expanded to any data set at all. And what we're able to do here is we're able to translate the distance from the mean into probabilities that can be used to interpret data. So those probabilities are the percentages that we've been looking at. And we can do that by using our normal distribution tables, which we're now comfortable with. But what we also need to understand is something called a z-score. And that's what we're going to look at next. A z-score is the number of standard deviations from the mean, and the formula for a Z-score you get in the exam. It's on the normal distribution table. It's in the top corner of the normal distribution table. And distances from the mean in the normal distribution are always measured by the number of standard deviations that they represent. And that's what we know as a Z-score. We're going to look at lecture example 7 that will help you understand how we calculate a Z-score, and that could aid your understanding in relation to meeting the final couple of learning outcomes for the chapter. Now remember that the learning outcome is not to calculate a Z-score, but the learning outcome is to be able to interpret normal distribution graphs and tables, and therefore having an understanding of Z-scores will help you to meet that learning outcome. Now we've already looked at the normal distribution tables. We've seen from them that it gives us a percentage, and the tables will show the relationship between the percentage of the population and the Z-score for any specific Z-score. And remember that we are provided with the tables in the exam. Let's look at lecture example 7 then, and we're going to use this just to help us understand what the normal distribution can be used for and what your normal distribution tables can help us identify. Okay, so here we're asked a few things. So there's 3 different requirements. It says, what is the likelihood that a student will drink more than 285 pints, less than 200 pints, and between 220 to 255 pints? So we're asked to identify the likelihood. So here we're looking to identify the percentage, and we're going to use the normal distribution tables to help us do that. So it tells us that the average number of pints of beer consumed in 3 months by an accountancy student is 251. So that 251 is our mean. Yep, so that's the mean that we're going to use to put into the formula here. And remember, the mean was denoted by our symbol U. So I'm just going to note that the mean is 251. And we're told that the standard deviation is 15 pints, which is denoted by sigma. Okay, and we're going to use the formula. So X in the formula becomes the data that we're assessing, or the number that we're looking at. So for example, in requirement A, 285 becomes X. Okay, so if we're looking to calculate the Z-score firstly, we can say that the Z-score is equal to, if we copy out the formula, X minus the mean divided by the standard deviation. So if we look at requirement A, X becomes 285 minus the mean, which is 251, divided by the standard deviation, which is 15. So the Z-score for requirement A is 2.27. Okay, and we want to take that Z-score onto our normal distribution tables to work out the percentage, or the likelihood, that a student will drink more than 285 pints. So if we go on to our normal distribution tables, and we're looking for a Z-score of 2.27. So if we go to 2.2 firstly, and then we read across the rows to 0.07, yep, to give us 2.27, we can see our number from our normal distribution becomes 0.4884. And that's what we're going to carry forward into our calculation. Okay, so it might be easier to show this as a normal distribution curve. So in the question we were asked for, what is the likelihood that a student will drink more than 285 pints? Now remember that the mean was 251 pints. We calculated the Z-score when we looked at the 285 pints, and the Z-score was 2.27. And remember that that Z-score is the number of standard deviations from the mean. So 285 pints is 2.27 standard deviations from the mean. We want the likelihood that a student will drink more than that. So we want the shaded proportion of the graph, if you like. We want the percentage that sits in this shaded proportion of the graph. And remember that the full side of the graph, so remember it's symmetrical, so it's 50% on each side. So this full side represents 50%. We took our z-score from our normal distribution tables, and we were given a figure of 0.4884 is what we took from our normal distribution tables. So if we take our 50%, 0.5, and the 0.4884, if we change our colour, would represent what I'm now shading in pink. Yeah. So in other words, 48.84% would sit within the shaded area. We want what sits outside that shaded area. So if we take the 0.5, if we deduct 0.4884, the percentage of students who will drink more than 285 pints will be 0.0116, which will be 1.16%. Okay, let's look at requirement B then, where we're asked for the likelihood that a student will drink less than 200 pints. In requirement B, we are asked for the likelihood that a student will drink less than 200 pints. So now we're starting to look at the lower end of the graph. We're looking at below the mean. So remember, the mean is 251, but now we're making x 200. So we need to calculate the z-score in relation to 100, or the chance that a student will drink less than 200 pints. So again, if we put it through the formula, where we take the 200 minus the 251 and divide it by the standard deviation of 15, we get negative 3.4. So this time our z-score is negative 3.4, and remember that's the number of standard deviations from the mean. So if we go on to our normal distribution tables at 3.4, we will see a figure of 0.49966. And remember that relates to our percentage, so 49.966%. What we are looking to identify is the probability of a student drinking less than 200 pints. So the area in the graph that I'm now shading in pink, if you like, would be 99.966%. Yeah, so we can see that the proportion that we're looking for here is a very negligible percentage. If we see through the calculation, it drops out at 0.00034, which is 0.034%. So 0.034% of students will drink less than 200 pints in 3 months' time. Okay, and then finally in requirement C, we are asked the likelihood that a student will drink between 200 and 255 pints. So this time we have to calculate two separate z-scores here. So you'll see that we are now calculating the z-score for 220 and the z-score for 255. So pushing it through the same formula, again the only thing that is changing is x. Yeah, so x minus the mean, which is 251, divided by the standard deviation, which is 15, will give us the z-scores that we are looking for. So negative 2.07 and 0.27. We take those z-scores onto our normal distribution tables to get our percentages. So let's just check them together. So if we go on to our normal distribution tables and if we look for our 2Z scores, so we had 2.07, yeah, which would give us a number of 0.4808 or a percentage of 48.08%. And then our Z score of 0.27 would give us a number of 0.1064 or 10.64%. We take that information back to interpret the data, and we therefore see that the probability of a student drinking between those two Z scores, so between the 220 and 255 pints in 3 months, if we add together the two percentages that we've pulled from our normal distribution tables, we would get 58.72%. The final thing that we're going to look at here is how we can start to manipulate the Z-score calculation to answer different types of question. And we'll use our final lecture example 8, to illustrate that. Here we're told that a normal distribution has a mean of 150 and a standard deviation of 20. We're asked 80% of the population is therefore below what? Okay, let's make it maybe a wee bit clearer then by using our normal distribution curve. So here we're told that the mean is 150 and the standard deviation is 20. Now we know that 50% of the population is below 150 and 50% of the population is above 150, but we're not asked for 50%, we are asked for 80%. So therefore we need to find 30% from our normal distribution tables. So let's look at the normal distribution tables and see if we can find what the Z score is at 30%. So if we go on to the normal distribution tables, remember that all of the 4-digit numbers represent the percentages. So we are looking for something close to 30%. So I'm looking for 0.30. So if I look onto the table, I see that the number 0.3023 is our closest representation of 30%. So that would give us a Z score of 0.85. Okay, so let's take that 0.85 back through to our calculation and see if we can manipulate the data to answer the question. Okay, so we said that 30% from our tables equals a Z score of 0.85. And then we're going to use our formula, and our formula for the Z score, again remember you get it in the exam, it's on your normal distribution tables, and it said Z equals X minus the mean divided by the standard deviation. And normally we plug in X, but this time it's X that we're actually trying to identify here. Yeah, but we do now have our Z score that we can plug in. So our Z score was 0.85 is equal to X, which we don't know, less the mean, which is 150, divided by the standard deviation, which is 20. And then we basically need to rearrange that equation so that we're left only with X on its own. And some of you might be really good at rearranging equations, some of you might not be so comfortable, so let's do it step by step together if you're not sure. Okay, so the first thing that I would do is separate everything out. So I would say 0.85 is equal to X over 20 minus 150 over 20. And then my ultimate aim is to be left with just X on the one side. So the first thing that I'm going to do is I'm going to add 150 over 20 to both sides. Yep, or in other words, I'm going to take this over to the other side. So I'm going to say 0.85 plus 150 over 20 is equal to x over 20. And then to be left with x on its own, I want to multiply both sides by 20. So I'm going to take 20 and multiply it by 0.85 plus 150 over 20, and that will be equal to x. If I take 20 and multiply it by 0.85, I get 17. Yep, so 20 times 0.85 gives me 17. And then if I add on to that, 150 divided by 20, but then multiplied by 20, would just give me 150. So therefore we can work out by rearranging the equation that x is equal to 167. So to answer the question, it said 80% of the population is therefore below what? Well, 80% of the population is under 167. And that would be our final answer. Let's summarise Chapter 4b. We looked at both grouped and ungrouped data, and remember, grouped data is where we show the information in terms of a range or a class, whereas ungrouped data is where we show the individual specific items or values. You then need to be able to do 3 calculations. You need to be able to calculate the mean, the mode and the median. Remember, the mean is the average, and you get the formula in the exam. It's where you take the sum of all of the items and divide it by the number of items. So just a basic averaging calculation. The mode is the most frequently occurring item, and the median is the value of the middle item. You then also need to be able to calculate measures of dispersion, including the variance, the standard deviation and the coefficient of variation. You get a formula in the exam for the standard deviation, and you also need to know that the standard deviation is the square root of the variance. To be able to calculate the coefficient of variation, you take the standard deviation and you divide it by the mean. We then looked at calculating expected values. An expected value is a weighted average based on probabilities. And remember, you take the sum of the probability multiplied by the outcome. We finished the chapter by looking at normal distributions, and it's important that you're able to explain the properties of normal distribution and be able to interpret normal distribution graphs and tables. All of the areas covered in Chapter 4.b could appear in Section A of the exam as an objective testing question.